Hi everyone, my name is Neha and this is the 14th lecture on Introduction to Automation. In this lecture, we are going to learn about wound field direct current motors. Wound field motors, they uses an electromagnet, which is also called field windings, to generate the magnetic field. And these DC brushed motors, they are available in two types. First, wound field, second, permanent magnet. And they both types they uses current and windings to produce a magnetic field. But they differ in how stator magnetic field is produced, whether it is produced via permanent magnets when it is placed inside the stator, or it is produced with wound field windings. So this permanent magnet type DC motors we'll be covering in the next lecture. And right now we're going to focus on wound field DC type motors. The speed of these wound field motors, it is controlled by varying the voltage to the armature or the field windings. Now next we are going to see different types of wound field DC motors. The first type is the series wound DC motors, and you can see here in the picture the armature when it is connected in series with the field winding, then this type of arrangement is called your series wound DC motors. Here on the second picture you see series motor. When it is reverse, then the arrangement will look like this. And on the top here you see the voltage equation where VNL is the line voltage and it is the line voltage which is over here, and CEMF is the counter EMF and which is developed in the windings of the motor, and IARA is the voltage in the armature voltage, and IA is the armature current and RA is the armature resistance. ISC and RSC is the voltage in series which is developed due to this field winding, and this field winding is sometimes also called a series field winding, and that's why it is written over here ISE. SE stands for series, so current in series and resistance in series. So if you notice in this type of arrangement, our armature current and the ISE, they both are same because it is a series circuit. So the further if you solve this equation, then it will come out to be VLN is equals to CEMF plus, you can take either IA or ISC common. So let's take IA common. So IA, and in the bracket you will have RA plus IRSE. Now there are two important characteristics in the DC series wound motor. The first is the higher starting torque. So this type of motor has a higher starting torque, and higher starting torque is needed in the car. When you start the car, it requires a higher starting torque. So there this DC series wound motor is very useful. And how this higher starting torque can be achieved, we will see now. So what will happen when the motor is stopped? Then at that time there will be no counter EMF will be present in the motor, and at that time the full line voltage will be available to the winding. So the initial armature current flowing into the motor, it's going to get large, and that large armature current, it will produce the large magnetic field. And as you can see through this torque equation, where torque is directly proportional to the armature current and the flux, so combination of the armature current and flux will produce the large torque. So that's how we get the large starting torque. And eventually if the torque increases, then after some time, then the counter EMF in the motor, it will also produce, and it will try to oppose the line voltage, and then ultimately what will happen, the torque will also get reduced. So here we see that the starting torque is high, but eventually as the motor runs, the torque goes to a normal value. Now the next important characteristic here is the DC series motor, it run away, or we can say that it goes faster and faster when there is no load. So it is based upon this equation. So what will happen when you do not have any load attached to your DC motor? Then what will happen? The armature current which will flow into the motor, it will produce the magnetic field, and further when the magnetic field is produced, torque will be created, and then at the same time your counter EMF will also increase, and as the counter EMF increases, then it will tend to decrease the field current, which is your motor current. So this, when this field current reduces, then our magnetic field, this phi is your magnetic flux or magnetic field, you can say. So your magnetic field also it will reduce. So when it will reduce, then what will happen? You can see through this equation, if the flux is reduced, magnetic flux is reduced, then the speed will increase. You can see there is an inverse relationship between the magnetic flux and the speed. So if the flux is reduced, then the speed will increase. And if the speed is increased, then you see the proportional relationship is with the counter EMF, which means the counter EMF will increase, and when the counter EMF will increase, then again your flux will get reduced. So this cycle you see here, it will go on, and this overall effect of this seemingly circular logic is that the motor will continue to accelerate until the torque is balanced by the friction force. So most smaller motor, they can handle the high speed without causing any damage, but when you are working with the large motor, then they may literally fly apart if they are operated at a no load. Now let's see the torque speed curve here. So you can see the torque is on the horizontal axis, and speed is on the vertical axis. And if we see the relationship between these two, then we observe that when the speed is high, at that time the torque is very small, whereas when the torque is high, at that time the speed is very small. And here you see this stall torque. What does it mean? It means that when the maximum torque the DC motor it delivers, at that time whatever the torque is, that is called your stall torque, or you can say that your maximum torque. So when this occurs, the motor is actually loaded, and it is loaded so much that it comes to a stop, and that is called your stall torque. And this stall torque is actually desirable in some of the application. For example, in robotic arm, if you want to put something from one place to another, so in that situation the stall torque is actually required. So that is one of the application where this can be used. Now here if you see at this point, when there will be no load, the speed is going to be very high, and when the speed is very high, at that time the torque is going to be low, or you can say it will be zero in this case when the speed is at this position. So this large DC series motors, they can be damaged if they run without the load. So you need to avoid that situation, running a large DC series motor at no load. And now let's see this current curve. You can see this current curve. As the torque increases, the current also increases. The reason why, because they have the proportionate relationship. You can see here the torque is proportionate to the current, armature current. So as the torque increases, the armature current, this current will also increase. Now next we have DC shunt wound motors. So the DC motors in which the armature and the field windings, when they are connected in parallel, then they are referred to as a DC shunt motors. And the variation in construction between the series wound DC motor, which we have seen previously, and between the DC shunt motors, they result in some differences in their operation. And the most significant difference basically lies in their speed characteristics. So these DC shunt motors, they are able to maintain a constant speed regardless of the load on the motor. And because of their self-regulating speed capabilities, these DC shunt motors, they are ideal for application where precise speed control is required. However, just keep in mind that they cannot produce high starting torque. So the load at the startup, they need to be small. And the application where these type of motors can be used, it includes machine tools like lathe machine, in grinder, in industrial application. It is used, for example, in fans and compressors. They can be used. And here on the screen, you see these equation which has been obtained from this circuit. So in this, the total current which is going over here, this is the total current, and that total current will be the combination of the armature current which is going to this node, and the shunt current. So by Kirchhoff current law, we have obtained this equation, and this ISH, which is the shunt current, and shunt current is here. This shunt current is equals to VLN by RSH. At this node, the voltage is VLN. You can see here, this at this node the voltage is VLN. So VLN by RSH is the shunt resistance which is produced due to this field winding, and that's how we got this equation. And then the line voltage equation, it can be written in this way: VLN is equals to counter EMF plus IARA. Here this counter, so here in the next equation, this IA, this can be written in this way: I total minus ISH. So that will be your final equation. Let's see the curve between torque and speed, and you can see here both stall torque and the no load speed are relatively low when compared with the DC series motor. So this DC shunt motor, it will slow down when the load increases, and it will speed up when the load decreases. Now here, when you have a fixed line voltage, the speed can be controlled by inserting a rheostat over here in series with the field winding. And if you insert a rheostat here, with the help of that, you can control the speed. So what will happen, as the resistance of the rheostat, it will increase, then the current to the field winding, it will reduce, and which reduce the field flux. And as the field flux reduces, then it will speed up the motor. This is the way the speed can be controlled. Now let's see next, which is the compound motor. And in this compound motor, it will have both series field winding and the shunt field winding. As you can see in this circuit, it has both of them. And this type of arrangement is called short shunt. And this type of arrangement, where the series field winding is in series with the armature, and shunt winding is in this way, then this is called your long shunt. Now here, the main purpose of the field winding is to give the higher starting torque. And once the motor is running in this type, then the back EMF will be produced, and that back EMF, it will reduce the strength of the series field, which leaves the shunt winding to be the main source of field flux, and thus it provides the speed regulation. So that's why these two windings are used. Now if you see the torque speed curve, then you will observe that the combination of a series field and the shunt field, it provides a linear portion in the torque speed curve, and which is very useful. And here the equation which you see here, it is based on this circuit, and this is a short shunt compound motor. And in this, the line voltage will be given by this equation, which is equals to counter EMF plus IARA plus I total RSE, which is the series resistance. This is your series resistance. This is your shunt resistance. Current flowing here is the shunt current, and current flowing in the motor is the armature current, and the total current is this one. So this series current here is the same current, which is the total current, and that's why I've written over here. So this will be the equation for short shunt. And now let's see the application. The application of compound motor, they are used where higher starting torque and fairly constant speed is required. So for example, in the elevators, rolling mills, presses, heavy planners, in all these applications this can be used. So this is the end of the lecture. Thank you so much for watching.